So now we're starting a new chapter, and one thing you'll want to have handy for while we're working on this one is the reference sheet I'm giving you guys. These are not formulas we're going to make you memorize all of them. In general, you will be able to use these on assignments and tests and quizzes. There might be a few, though, that are definitely worth memorizing, and I'll point those out to you. So the goal in this section is using the formulas on that reference sheet, or the trig identities rather, to rewrite expressions into simpler terms. So basically we're going to try and take some big ugly expression and then break it down into just one or two terms rather than 4 or 5 terms with higher exponents. Now, as a comment on this, there is no one method to verifying the identities in general. There are often lots of ways you could approach the problems. Some methods just may end up being easier or taking less steps than others. These are the guidelines we're going to be looking at over the next couple sections of notes. Today, specifically, we're just going to look at rewriting terms using sine and cosine functions and doing some factoring. We will also do some work with fractions as well, but some of the other things we'll come back to in more detail later on. So first, let's just talk about the strategy of rewriting terms using sine or cosine. What you want to do is look for any cosecants or secants and make sure you remember how to rewrite those since they're the reciprocal of sine and cosine. So if you see cosecant, you would instead rewrite it as 1 divided by sine. Just make that substitution into the expression you see. Similarly, for tangent and cotangent, make sure you remember tangent is sine divided by cosine, and cotangent is cosine divided by sine. So again, those would be substitutions you perform, and then hopefully some of the sines and cosines will cancel out, or you'll find something that you can factor as a result of doing that. So the idea is that you should not see any secants, cosecants, tangents, or cotangents in your expression. So here's our first example. Now, like I said, we don't want to see any of the cosecants or tangents in there, and I see both right now, so I need to remember that cosecant is the same as 1 divided by sine, and tangent is the same as sine divided by cosine. So I'm not changing any of the operations here. I'm still multiplying these two terms. I've just replaced cosecant with its reciprocal and replaced tangent with the sine and cosine relationship. Now, initially, I didn't see any way to break this down into simpler terms, but by rewriting it using sines and cosines, I now notice that the sine in the denominator and the sine in the numerator would cancel when I multiply these together, which would mean I just have the function 1 divided by cosine of x. Now, this is pretty simplified, but if I wanted to make it even easier to write so that there isn't even a fraction left anymore, I could go back to the reciprocal functions and remember that 1 over cosine is the same as secant of x. And so this seems as simplified as it could get. There's no way to break a single trig function down into something smaller than that. So the idea is to take an expression and somehow reduce it to something easier or smaller to work with. Here's another example where I have some sines and cosines, so I'm going to leave those exactly as they are, but I'm going to take the tangent and rewrite that one. So my expression says sine of x times tangent, but I'm going to rewrite that using the property sine over cosine. And then again, this one's already set up as plus cosine, so I'm going to leave that as is. Now, nothing canceled in this case, but if I think of this as sine of x over 1, then I could multiply these two fractions together to call it sine squared of x, or sine of x squared, it's just another way of writing it, divided by cosine of x. Now, the problem with trying to add fractions is that you need a common denominator. And right now, my other term is cosine of x over 1. However, if I took that expression and multiplied it by cosine over cosine, that would give me a common denominator. Remember, the reason I'm allowed to do this, multiplying by cosine over cosine, is because technically cosine over cosine equals 1, and multiplying by 1 does not change the value of the fraction I have. So multiplying this by 1 means I have the same value, but now it's going to be in a form that lets me combine the two fractions together. So cosine of x times cosine of x will be cosine squared, just like x times x is x squared. My denominators match, which means I can write this as one fraction, where the denominator is just cosine of x, and the numerator is now sine squared plus cosine squared. At this point, we need to use our reference sheet that I was referring to earlier, and I'll point out exactly which formula I'm going to use here. The Pythagorean identities, you want to look for these whenever you see some of your trig expressions being raised to the second power. So if you see some kind of a combination of sine squareds, cosine squareds, or even the ones down here like tangent squared and secant squared, or if you see one of the functions squared and a 1, there's usually going to be a way for you to manipulate one of these formulas and perform a substitution to cancel some of the information out. In this case, I specifically have sine squared plus cosine squared, which is nice because those two things combine to equal 1. So that means I can perform a substitution here on top. Sine squared plus cosine squared is equal to 1. So if those things are equal, I can replace one with the other. So now I just have 1 over cosine of x. And again, this is almost done, but if I remember that cosine and secant are reciprocals, then I don't even need to have a fraction anymore. I can just write secant of x. So to recap, we started off by replacing things with sines and cosines. Then, if you have a fraction in one term, but not in the other, you might want to find a common denominator, which will allow you to combine them into one property. If you see any trig functions to the second power, then check your Pythagorean identities especially, see if there's a substitution you can perform to break some of that down. And then don't forget your reciprocal identities as well, the ones we've been using since the last chapter. Next, let's talk about the strategy of sometimes factoring to cancel out some terms or reduce things. The most common factoring you'll need to use is the GCF. So look for sine of x, for example, in multiple terms. If you see that, then try to factor it out of every single term by writing it out in front of the parentheses and then taking it out of all the terms you factored it out of. You can also still use trinomial factoring or even difference of squares, just like you do with other expressions. The factoring works the exact same way, but instead of having x squared, you'll have something like sine of x squared plus 3 times sine of x plus 2. However, the factoring would break down the exact same way as far as you being able to say, okay, well, you need two numbers that multiply together to equal 2, but add up to equal 3. So instead of writing x plus 2 and x plus 1, you would be writing sine of x plus 2 and sine of x plus 1. So it doesn't really affect much other than the fact that you don't just have the single variable, you have the trig function there. So let's look at a couple applications. Here we see two terms. There's cosine of x, and we're subtracting cosine of x times sine squared. So in these two terms, they do have something in common. They both have a cosine of x in them. So that's what I'm going to factor out. And then inside the parentheses, I write what's left when I remove the cosine of x. So cosine divided by cosine is 1. And cosine times sine squared is just the sine squared value. Again, anytime you see a trig function being squared, or if you see two of those happening, or if you see one of those happening with a 1 combined with it, check those Pythagorean identities again. So here's one that has a sine squared of x and a 1 in it, but right now things are not set up in the correct form for me to utilize this. However, this still works like any other equation, so I can manipulate it to my advantage. If I subtract sine squared from both sides of the equation here, then on the left-hand side it would cancel out, and on the right-hand side I would end up with 1 minus sine squared. Now this is more useful to me because now I see that 1 minus sine squared of x is equal to cosine squared of x. So don't forget that you can use your algebra solving operations to manipulate these around to your advantage. So I'm going to replace the 1 minus sine squared with cosine squared in our example. I'm not doing anything to the cosine of x I have out front, but now that I have it in this form, I can redistribute, if you want to think of it that way, or just multiply these two terms together to call this cosine cubed of x. Again, multiplying the trig functions is the same as multiplying something like x times x squared, which equals x cubed. So it's the same procedure for that. One more example, I have two terms, sine cubed of x and sine of x times cosine squared. Again, there is something in common between the two of them. I can take out a sine of x from each term. So for the term on the left, if you take one of the sines out, you'll be left with sine squared. And when you take the sine of x out of this term, you'll be left with just the cosine squared. So here I see a sine squared and a cosine squared. So if we look back at our trig identities, and let's go back to what it looked like before I manipulated a bit, we have this one that says the sine squared plus cosine squared functions add up together to equal 1, which is very convenient for us because that's exactly what I have here. So instead I can write sine of x times 1. And really we don't like to write times 1 or divided by 1. It's an unnecessary piece to show there. So that means I actually just have sine of x. Multiplying by 1 does not change the value. So we've taken something that used to look pretty ugly and it would have been very complicated for us to compute with an angle like pi over 2 being thrown in there, for example. But now we've just established that that answer is actually always the same as just taking sine of the angle, no matter what the angle is. So this is a lot easier for us to work with, which lets us more quickly find the answer and be more efficient in our work. So that's all for the notes today. We'll come back and look at other strategies for breaking down some of these various expressions in the next section. Thank you.